this should please the bore. Certainly are live. All right, and good. Yeah, we're live. All right, so let's close that now. All right, guys. So all right, now, so for this lab now, guys, I will say, and I will say it once more, that we place a hot metal into a room temperature container with water. All right, so what's gonna happen is the hot metal will lose the heat, and that's why I write the statement here. All right, if you can zoom in to see the statement right here, and I'm going to highlight it in red here, that the heat lost by the metal is equal to the heat gained by the water and the calorimeter. All right, so this metal was it came in at about 90, so I say about 98 degrees there about. The data will tell you that anyway, so let's go back to that data to see what should be in that. It's actually 98.6 degrees. So the metal came in at 98.6 degrees. And when it went, and when it entered the calorimeter with the water, some of that heat went towards it. And so what happened is that the temperature of the water and the calorimeter before, and it's actually here as 19.7. So 19.7 was the temperature there. So this is pretty cool. Usually the calorimeter is cool because it does such a good job at keeping out heat from it. So that's why it's used. So water is in there at 19.7 degrees. So as the law of heat suggests, I believe that was given to you, is that heat will always flow from from a hotter object to a colder one until both objects reach the same temperature. This same temperature here, and this same temperature here is referred to as thermal equilibrium. That's the term that qualified physicists would use to describe this thing. Body in the grade 1 ballpark would be using this term. Thermal equilibrium is when two or more objects reach the same temperature after exchanging heat with each other. So therefore, what should happen, everything should reach the same temperature in the end. So going back to that, all right, so what happens is that the final temperature of the water is going to be 20.6. So what happens, so that's the heat. Let's use a red marker to show that the heat would have left. Heat would have just left and go over here. And then what happened now, why it just go up? It just go up to 20.6. That's the final. And it just go up to 20.6 for obvious reason. The copper, the mass of the copper is small. So because it's small, it doesn't, have the capacity to store a lot of heat. All right, so it's a small piece of copper. So imagine that, guys, you have a hot cup of tea in the morning, and then, all right, so you're rushing to go. Maybe that was like before COVID, but all right, so let's say even now you're getting a hot cup of tea, you make it yourself or your parents give it to you, whichever way you get it. Some of you probably can't drink it too hot. So maybe your parents or maybe yourself decide that, well, let's drop a cube of ice in this cup of tea. Now, 1 cube of ice, all right, in a big cup of tea. How does that work now? Does it cause the tea to get cold?
A little bit cooler, depends on how much ice, sir.
But remember now, what did I say about the amount of ice we're putting in?
My computer froze, so I was kicked off, so I didn't hear anything.
Oh, okay. So I say that the 1 cube of ice in a wee cup of tea. Has anybody been to Starbucks?
Yes, sir. Top 10.
Oh, Shante, well done. Okay. Anybody else? No? All right. Anybody know what Starbucks is famous for?
King of coffee.
Coffee. Yeah. Coffee with your name on it. So yeah, definitely. All right. The point is that, guys, specific heat capacity is referring to how much heat a certain mass can hold. And the copper here, it was very small cube of copper going in a large calorimeter with water. So it only could let it go from 19.7 to 20.6. All right. But then the copper itself decreased significantly. As a matter of fact, let's use a red, a blue to show that the temperature of the copper came down to 20.6. So what's happening now is that, all right, so the copper gave up all of its heat to the water and the calorimeter. All right, I hope everybody understands what is happening here. All right, the lab was done last class and we are explaining what took place there. All right, so if you don't know what we're talking about, you go back and watch that video and find out that. But the point is that the copper went in very hot and into a larger container of water in a calorimeter. Calorimeter was at that time 19.7 degrees Celsius. And by the time the heat exchanged to it, it went up slightly to 20.6. While the copper itself, no, because remember that the heat will flow. And if we go back to that definition, the definition says that the heat will flow from objects of higher temperature to one of a lower temperature until both objects reach the same temperature. So that's what happened in this experiment there at 20.6. So the copper would have lost so much heat from moving from 98.6 down all the way down to 20.6. And then the water and the calorimeter together just increasing slightly to 20.6. So that's the story there, guys. But we're gonna put some physics to it now. The formula for heat capacity, going back to that formula, is actually this. So, and as a matter of fact, let's highlight this one and put in a tick there, and let's zoom in. So the formula for heat capacity, as you can see, is going to be what? The change, well, it's actually the energy. So this is the formula we're using. I remember that a common C represents specific heat capacity. So it's the change, or this you could say the energy. Sure why they put C back here again, but right, fair enough. Yeah, there goes the change in temperature times the mass. All right. So probably I should just maybe crop here. Yeah, because this part here, them look like them the foolishness here. So all right. Yeah, there we go. That's what we're using. Specific heat capacity is covered here. So it's gonna be the energy transfer divided by the mass times the temperature change. That's the one we're using. So let's go back to what we have here. And seeing here is just that. All right. What's gonna happen here? I put each of them in different colors for you to see what's happening. The metal, everything we're working on for the metal is in black. Everything we're working on for the water alone is in what looks to be a pink or lavender type color. And the calorimeter here will be done in blue. So we're keeping the color scheme consistent. What's going to happen is this. Notice that this story in red is saying, all right, let's probably use a deeper tone of red, maybe. If I can find that. Yeah, heat lost by the metal is equal to heat gained by the water and calorimeter, which means that when you add the two of them, so we add whatever we get for the water. All right, we add it to whatever we get for the calorimeter. All right, so let's deal with them piece by piece and see what happens. We'll say, all right, so I have here 69.93 times 4,186. And of course, we're multiplying that by the difference between 20.6 and 19.7. So just simple maths there will tell us that 19.7, taking that number away from 20.6 should give you a 0.9. All right. And of course, we are going to multiply 4,186. And again, we're going to multiply it again by 69.3. And we get some number here that we can use to complete this. So when you do that now, you get a calculator, right? Which I'm really hoping everybody know how to use their own. So it should be 69.93 plus 4186. All right. And that should give us, and we also multiply it again by 0.9. As a matter of fact, did a little foolishness there. So let me just fix that out. That's yes, calculator. All right. So go again. 69.93 times it's gonna be what, 4186 times 0.9. All right, and this should give us there is a one figure here. It's 2,000 or 263,000. And you could even just cut and paste that as well, but well, all right, 263,454. And of course, some decimal place there. We probably want to add those so that we can increase the accuracy here. All right, so it's gonna be that number, 9282. So let me ask you this. Doing this was what you got for your own?
Yes, sir.
Okay,
Yes,
so
sir.
all right, so no problems there. All right, so going back up, then we're going to add the calorimeter. What happens to the calorimeter? So what this number is, you know, guys, is the energy. It's the energy that the water received from the metal. All right, this number works out to be 263,454.282. And then what we're gonna do now is work out what happened to the water. Or rather, is this the calorimeter then blue? Yes, the calorimeter. All right, so remember that because the water is in the calorimeter, both of them going to have the same temperature eventually. So this 20.6 minus minus 19.7 will give us the same 0.9. So let's get into our calculations here. 0.9 will be there. And of course, we have 387. And we also have 39.53. All right. So that's the situation there. All right. Now, guys, again, calculator comes into play here. You get simple maths to do here. And 300, let's clear that. And let's go we could say 0.9 times 387. All right, times 39.53. And you're getting something like 13.9. which is not much really. It didn't get much from the block, so the water took everything. All right, let's see. The water took most of the heat energy, guys, from the metal block, and it has to do with the, well, let's see, that's probably to do with the mass of it and the heat capacity of it as well. The calorimeter cannot hold a lot of heat, so let's go back to these figures and see what we get. 13,768. So 13,768 and 0.299, I believe, was it? Yeah, joules. So all right, so then we're almost there. We finished one side of the problem. We just need to add these two now. 13,768. We add that to what we get before. These two numbers we're going to add. So okay. All right, so let's cancel that. Let's add plus there. And okay, that becomes 0. And that's allowing us to paste there. It's interesting. All right. Okay, I'm paste it. I think I'm paste it. All right, let's put it in there then. All right, so 263. And I mean, it's just a shame that I have to be doing this because you guys could do this easily. All right, let me just run this in. 263, 454, and then we go 282. So yeah, 282. I'll add them together. So they're 277. So that's your answer for that part. Yeah. Copy this answer there. All right, color that. All right, so here's our answer. Partially, we get one side of the equation. All right, so we're going to have to carry down this part now. So I must come in like an accounting sheet. You have the ledger, you know. All right. So anyway, so we have 8.9. So this is the case now. We have 8.9 over here times CM times, we take away 20, 20.6. All right, so this is going to have a negative number as remember the final temperature minus the initial temperature is the temperature change. So the final temperature was 20.6. When I take away 98.6 from that one, and so that should easily give us what's that, 70? 78. That should give us 78. Didn't think I need calculator for that one. It was easily give us 78. But it's negative 78. All right. And so when I go again, we'll have it's carry this back down to 0. So negative 78 times 8.9. And that'll give us 694. So 694 times CM. All of this that we just calculate. Let me see if I can select all of that. All of this we'll just get. In fact, I'm gonna group this too because yeah, I'm gonna carry it down here. So now this is what we have here. Final equation here. All right, so all of this now. So you notice it step by step we show you how we get the answer. And then now we have to solve for the specific heat capacity of the metal. Remember that CM is the specific heat capacity of the metal. All right. C, small c stands for specific heat, and then Of course, the M stands for metal. All right. So that is what we're doing here. All right. So now we're going to find Cm by simply dividing this number. So we could just copy this number and show how we divide it. All right. And then we just, this thing actually moving slow. All right. When we put this number, then we just use a smaller font or something. With about 12 maybe. We can get some more space. All right, so putting it right there now, and we're going to divide this by 694. So easily we can go back to our calculator now. All right, and I'm going to put this 277 that we get. All right, let's clear that. And let's copy back this number. Hopefully it will allow us to write it. Really? I paste the number. Oh, that's what we did. Okay. So when divide that by this number here, 694, and that's our answer. Yep, answer there is 399. That should be the answer. Let's just get the rest of the digits here. 0.45. So we could call it 60. But we can just call it 399.5. Really, that's almost 400. So yeah. All right. And of course, the units for specific heat capacity is joules per kilogram per degree Celsius. And then this will be negative. We're just giving that is negative. But then doesn't matter if it's negative, it's the same. The sign doesn't matter with specific heat capacity. So that's okay. So we have actually gotten the answer here. And this is where most of the marks coming from. So there's it, guys. Any questions?
No, sir.
No, sir.
All right, so I guess your answer now, Dwayne, was incomplete. So this is how you should have done it. All right, 399.45 should have been the answer there. All right, so let's go and look at that. Well, specific heat capacity of two different metals. We didn't do two metals. We're just going to do one here. So we could just simply say for the metal, that your conclusion, I'll read that. And then of course we'll change to was. Let's remove that E. And of course the units is there. Joules per kilogram per Kelvin. All right. And it's actually using the method of mixtures. All right, we can also remove this one as well. All right, so this 399 won't be here. 399.45. And in fact, you can put the negative there. And then of course, the right reflection after that. Precautions there stated, sources of error, and all of these need to be completed. Define specific heat capacity of the substance, stated units. So this was done in most, in more than one class before. Here it is, definition right there. Amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So you put that there. See. Yes. All right. So then that's page 5. All right. Explain the thermodynamic principles applied to the method of mixtures used in this experiment. Method of mixtures using thermodynamic principles. Let's go to our knowledge here. In fact, let's bring up the laws of thermodynamics. So, all right. And I think all right, find the simplest version of the laws then. All right. Wait, what? I missed something. Oh, yeah, I gave it this as the 0th law. So yeah. All right. So this is actually the 0th law then. All right, we just need this one then. I give it that. All right, so this would be on page 9. Let me just put that in the C page 9. Yeah. Heat flows from a hotter body to a colder body until they reach the same temperature. That's the thermodynamic principle. The method of mixtures using experiment. So compare results obtained with the established true values of the specific heat capacity of the metal. Let's singularize this one, of the metal used. All right. And compare the results here. What should it be? That's a question. And what did you get? So if we go on a simple Google search, we should see what, if we type in the specific heat capacity of copper, we should get a number. And that's what you're going to use. So you're going to compare the 399.45 with that one. So specific heat capacity of copper it is actually very easy to find here. It actually is 385 according to this at 25 degrees Celsius. So all right, now we know this well. Let me see something on this image. In fact, let me show you the evidence then. This probably might be on page 10. Let me show you something there. This is what you'll see on the internet. And let's close that. All right. Let's scrap out of this. We don't need all that. All right. Now, this is joules per gram per degree Celsius. So what that happens is that if we were to multiply it by 1,000, then you get 385. So that's according to that. 385 joules per kilogram per Kelvin or degree Celsius. So 385 is the value. That's page 10. Let's put that in the lab. So that here true value is C page 10. And then true value is actually 385 and we got 399. So a couple of degrees off, but working with it same way. Close enough. Joules per kilogram per degree Celsius. So what you would basically say here is, all right, so we get so it's the experimental value minus the true value, which right, the true value would be so you would say something like it's 399.45 minus, and it's when they compare, it means they're going to say which one bigger, which one smaller. So 399 is the experimental value. All right, experiment. The true value is what is done in the most most accurate scenario or most accurate environment. You will get 385, and it doesn't have any decimal point as far as we see. So therefore, this is the true value. So the comparing them, it shows that this is a little bit more. We want to find out how much more, so we have to subtract it. when we do that, take away 385 from 399, you know, we should end up with something close to 15, or I suppose, yeah, or 14, maybe 14.55, or is it? Yeah, all right. Not waiting on you guys to tell me that. Just leave it in my head. All right, so it's 14.55, I guess. Degrees Celsius. Or not degrees Celsius, but then there's just a difference of that. Joules per kilogram per degree Celsius. That's it. All right, that's it. I'm gonna say there is a difference. A difference of 14.4, 14.55. Which a possible experimental error. Error or limitation. All right, so that's it. And all right, source of error. Source of error now. You know, we pass source of error here, but we can say like right, because I'll a lab app and so now you have right algorithmic error in the all right, algorithmic errors in the app. But then of course also algorithmic limitations. So because the software can it can simulate the temperature of the surroundings. So there's a lot of limitations, you know what I mean? And then of course, let me say possibly heat loss to surroundings. Remember, we transferred the hot metal to the calorimeter, so some heat would have been lost there. So possible heat loss to surroundings. In fact, unavoidable. That's what we put. Unavoidable heat loss to surroundings. And of course, algorithmic limitations. Yeah. So this lab is just straightforward. You just need to write a reflection where you learn from the lab and how it can apply to your life. And that's it. This lab is through, guys. All right. So if you don't ask the questions now, well, no need to ask them later because I am finished with this. This is dead. This doesn't need anything more than you just writing it up. And if you don't write it up, if you don't write up everything by the end of the month, then I guess you might want to consider deferral. That's up to you. But so far I've seen labs from doing, see some progress there. You can see a few labs from your what is that? Deborah. But then sure there. And so the rest of you, I guess, I don't know, probably waiting on God to come and I don't know, wave a magic wand or something. All right. Anyway, let's get this out of the way, guys. This lab is finished. Any questions?
No, sir.
All right. So this was going to send in the group. All right. This was going to send in the group, and the rest is history. So this is today the 27th. And of course, this should be in the physics division. All right. And that's final. All right. Yeah, there it is. And no, that's in there. I don't want. All right. Hold on a sec. Where is that? Where's the physics group? This group is we don't. All right. Yeah, so there it is. So now, having done all of that, students, all right, as a matter of fact, let me send this to. All right, so. All right, so having done all of that now. All right, and we see we're in there ask questions about this same thing. From 20, what is that? Which year this? 2013 paper that. All right, 2013 this, and these are the questions I asked. That's 2013. Before we even get to do that though, Dwayne, let me see something. Your own. So I confirm something with your own. All right. All right. So this is out. So this is out. This number where you get here. That's out. You don't put your thing them in a bowl. Put your heading them in bowl.
Yes, sir.
That's how I gave it to you. So you keep the same format for consistency. All right. All right. So anyway. You combine the specific capacity amount that here. All right. Well, let's work with that then. Define the capacity, work this out, substitution. I don't know what happened here. Hold on a sec here. Hold on a sec. Okay. Let's see the 8.9. I did the kilogram conversion here. All right. Yeah, it's supposed to get 399. So let me see what happened with your own. Yeah, okay, so you got the 277 here. All right, so yeah, I get the mark for that. I get the mark for that. No, you're saying I get the 277. So all right, let's just see what you do now. All right. No, this is incomplete. This was 277 now. Would that be equal to I have a metal here. So this is incomplete. It's incomplete, man. Right, so this was incomplete. So we have to go look on the one that I send you here. One I send in the group supposed to can help us sort out that for the calculation.
Yes, sir.
All right, I'll accept this as a source of error. Precautions good. Beyond conclusion. Reflection. All right. Certainly at least get 1 out of 2 for this, even though the conclusion there, the answer will be wrong. So you have to fix the answer there. So that's what you have so far. All right. So not much to do here. Just yeah, not much to do there. So just get the calculations and the I guess I gave you a limitation, and you probably can add the second source of error. Let me just and that's it. All right. So and so this is, I mean, this is the beauty of when you type the lab, so easy to mark here. Just send it, open it, and it's done. You know. All right, these are 27 after 4, 21. All right, did know. So I'll send this back to you now and you make your adjustment. This one like
Yes,
this.
sir.
I don't like it saved though. Hold on. Well, hold on a sec. All right. No. Doing. Can't find. Oh, all right. Okay, got it. All right, so that should be there in your inbox. All right, guys. So that's it. So now, as I say, now next class, now as I say, and understand this though, that the labs are used to teach the content from the syllabus. So exams do come in labs, and so going through the labs like this will help us to be able to calculate these questions when we see them. So we have quite a few questions and specific heat capacity here, as you can see on the screen. Question B here, but the question that they asked in 2013 carried 15 marks, and it started out by asking you to define specific heat capacity. All right, so that's a common question, and they even ask for the symbol. Of course, you have heat capacity, which is different from specific heat. So I did say that last class. So those who heard, those who didn't hear, may the Lord help your ears to open. And we also, this same topic comes with gas laws. So it's in the same type of question where they would ask gas laws as well. General gas law, you should be able to state that. We did this already. So just like a recap here. All right. Of course, not in the habit of repeating myself, because learning must take place and students must take charge of them learning here. But this is the question that similar to what we did in the lab here. All right, so it's a matter of doing this question. All right, it's almost 8, but we'll continue this next class. Next class, now we can look at another type of question that they could ask, but then this time it will be more along the lines of radiation. That's where they, so yeah, with this thermal physics, they could go radiation, they could go heat capacity, they could go gas laws, and they could go with thermometers. So those questions, if they come, you should be able to do them. So next class we talk some more about that and look at some examples of those. All right, guys. So I'll actually see you next. Yeah, I'll see you when Thursday. See you guys on Thursday, guys. And thanks for coming out this evening. Enjoy your evening. All right.
All right, sir.
All right.